ABCD with BC parallel to AD. So how should I draw this? Whoops. Like that, then I draw a parallel line. Didn't mean to do that. Okay. All right, so a couple ways we can draw this. And then the points B prime and C primes are, so we take the reflections of B and C with respect to CD and AB. All right, so let me shrink some stuff a little bit to make it look nicer. Oops. All right, let me reflect. That's B prime and C prime. So let's make it so that we can see them. See. Maybe like that. Okay. Prove the midpoint of the circumcenters of the segment joining the circumcenters of those two triangles is equidistant from A and B. So first, I'm going to draw in a few things. So, yeah. Basically, triangle ABC prime is congruent to ABC, and BCD is congruent to B prime CD. Maybe it might look better if BC was longer than AB. So, like, what if I feel like that kind of might look a little more elegant, but what do you think? Which way is better? I'll move it back to the old way. Actually, maybe like that. Okay. So I'm going to draw the circumcircles. ABC prime. Okay, so that circle's basically ABC prime is congruent to ABC, and B prime CD, we know that's congruent to BCD. So let's draw in the centers of those two circles. So we have center of C and center of D, and we want to take the midpoint. Midpoint of E and F, which is G. That doesn't really look equidistant from A and D, so maybe I messed up somewhere. Ah, it is. I don't know why it didn't look like it. It almost looks like it passes through E and F, but no, it doesn't. That circle. Okay. So, yeah, let's draw it so it doesn't look super symmetric. Okay. So yeah, what does that mean? The midpoint of those segments is equidistant from A and F, A and D. So that's like the reflection. Kind of interesting. So, I mean, basically, it means if we like take the midpoint of AD, then it means G. It's like saying GH is perpendicular to AD, right? So yeah, E is the reflection of the orthocenter of ABC over AB. Let me draw the orthos. Let me draw. Yeah, the circumcircles of ABC and ADC. So yeah, there's going to be a lot of circles here, but oh well. So let's just see how that looks. Center of E and center of S. Okay, so it's like we take J and we reflect it across AB and we get E. And then we take I and we reflect it across CD and we get F. Wait. J and I. Wait, I didn't. There's something I didn't do right here. So wait, I should be taking the of BCD. It looks a little messy, but let's see. So because those two circumcenters, so yeah, I might delete it, but I just want to check it out for a second. It's like they almost overlap. Let's make it so that they're a little farther apart. So I and J are the circumcenters of BCD and BAD. They both lie on the perpendicular bisector of BC. And then we're reflecting them over AB and CD. And then we want to show that so, whoops. So EJ or EI is perpendicular, and we can, and they pass through the midpoints. So yeah, it's kind of interesting. We have like 3 perpendicular bisectors. So the perpendicular bisector of EI passes through A. The perpendicular bisector of FJ passes through D. And we want to show the perpendicular bisector of AD passes through G. Huh. Interesting. So what does that mean? Maybe we can find congruent triangles. Is triangle GAE congruent to GDF? No, I don't think so. But maybe there's some other congruent triangle. So yeah, let's see if we can find some congruent triangles. So it looks like GK equals GJ. I think that's probably pretty important because maybe GAK. We know GE equals GF by definition. It looks like GK equals GJ. Let's see. Oh no, that was just that configuration where it looked like it. Is GH? Oh yeah, GH would be tangent. Yeah, this is a tricky one. So we have a midpoint. So yeah, whenever we have the line connecting the centers of two circles, sometimes we can use Casey's theorem. Let's see. I wonder what the radical axis of those two circles is. So let's see if we can see, if we draw GB, are GA and GD tangent? It looks like it from this. No, they're not. I got tricked. GA and GD are not necessarily tangent. So yeah, how can we show that? Is there like a circle? So I mean, one way we could try to show A and D have the same power with respect to this circle, centered at G through E and F. And I wonder if we can use Casey's theorem. Let me draw. So it's getting a little messy, but I have an idea in mind. So let's see. Thanks for rejoining, Hakan. So we're on our third problem. Kind of a messy diagram, but it's not that complex of a problem. So yeah, it's kind of interesting. So that's the radical axis of those two. And this, that's the radical axis of those two. I think the distance from A to MN would be equal to the distance from D to OP if the problem were true. Let me check that. This is so messy. If this doesn't work soon, I'm going to start deleting stuff, but I want to try it for now. Those almost look parallel, those lines. Like I feel like those lines are MN and OP parallel. It feels like it, right? So let's see. So let me measure. This is one hell of a crazy idea, but it would be awesome if it works. So AQ is 1.6, DR is 1.6. Yeah, so basically by Casey's theorem, and I'm gonna try to do a video on Casey's theorem soon, but yeah, it is scary, isn't it? And I doubt that the proposer thought to solve it this way, but whoops, I just want to delete the measurement, not the. If I can show the distance from A to MN is the distance from D to OP, then that would solve the problem by Casey's theorem. And it looks like MN is parallel to OP. let's see. So I think, is it obvious that MN is parallel to OP? Whoops. MN is perpendicular to EF. So MN is perpendicular to EF, and OP is also perpendicular. So yeah, so MN has to be parallel to OP. And is the distance from A to MN the same as the distance from D to OP? If we can show that, that would solve the problem. I don't know if that's as hard as the original problem. Maybe it is, but well, so I mean, basically, yeah, what is that saying? So MN and OP are two parallel chords of a circle. And we want to show the distance from A to MN is the distance from D to OP. What does that, yeah, what does that mean? Yeah, first of all, our triangles MAN and PDO, I don't think they're congruent. $7.3, no, they're not congruent. Does AQ equal AH? No. So, I mean, yeah, it seems like it would probably be at least as hard to show that those distances are equal as it would be to show AG equals DG, right? Maybe those triangles are congruent. So does GQ equal GR? No. MP and ON are equal. Is that obvious? MP and, are you, well, oh, because it's an isosceles trapezoid. Oh, do you see a way to solve it? You said, I guess this works. Yeah, so MPON is an isosceles trapezoid, right? Yeah, I think maybe I was just too excited to use Casey's theorem, but yeah, I don't want to focus on this too much longer if it's really just making things more complicated. Let's see. But I mean, it doesn't seem that unnatural, right? You want to show the distance from A to the radical axis of those two circles is the distance from D to the radical axis of those two. I wonder if I could use Casey's theorem another time, actually. Like, what if I use Casey's theorem on point B? So the difference between the powers of B with respect to those two circles is twice EK. I think it might work, but it might be kind of a long dash, to be honest. I'll just start deleting some stuff, see if I can find a different way to do it. I'm kind of very sentimental about Casey's theorem, but I realize that that might not be the best way to go. So let me draw the midpoint of BC. So J, I, and M are collinear. And then we reflect I across AB and J across BC. So is MIGH a parallelogram? I don't think so. It's almost one, but not quite. But maybe. So I wonder, what if we reflect J, well, MI doesn't actually pass through D. That's just, yeah, a trick. Okay. Sec, guys, I'll be right back. All right, I am back. So yeah, not a complicated problem statement, it feels like. Hey, Sai, thanks for joining us. We're on our fourth problem today.
Hey, Michael, is there any time left? I was a bit ill, so for a week I got absent.
Oh, it's all right. Yeah, I hope you're feeling better. So yeah, we have an hour and a half left, so there's a lot of time.
Okay, cool. So can you explain the question that is going on? Just for 1 or 2.
So we start with the trapezoid ABCD. So BC is parallel to AD. And then we reflect C across AB to get C prime. And we reflect B across CD to get B prime. And then E and F are the circumcenters of these two circles. So ABC prime and CDB prime. So these two outer circles, the circumcenters are E and F, and G is the midpoint of EF. We want to show GA is equal to GB. So I drew in a bunch of extra stuff, but that's the original problem. It's not, it doesn't seem like a super complicated problem statement. So yeah, let's see.
What is point H that you made in bottom in line AD?
I define H to be the midpoint of AD. I just thought it might be useful, although it's not actually in the problem. But actually, so BC, CD, and HM are concurrent at a point. Maybe that helps. Yeah, what if I draw that? I don't know. I'm not 100% sure it's going to help, but let's see. So those three, there's like a point of concurrence here too, right? So what was point I? Oh, I and J are the circumcenters of ABC and B and BBC. So BD, AC, and HM actually have to concur at a point by Cheva. Maybe that would help. Are they the reflections of E and F across A, B, and CD? Yes, actually, yeah, they are the reflections of E and F across A, B, and CD. Yes. Yeah, let me actually so yeah, HM has to pass through the intersection of the diagonals. And you can prove that in a couple ways. Cheva's theorem or similar triangles. Is GNAB cyclic? No. Let's see. So yeah, there's a couple ways we can show GA equals GD. We can find some congruent triangles. But the thing is, it doesn't look like GEA is congruent to GDF. But maybe there's some other congruent triangle we can find. Let's see. I don't think, does GB prime equal GC prime? Is that true? No, it almost looked like it, but yeah. It's tricky. Okay. JDFC and EBIA are parallelograms. That sounds like it might be helpful. JDFC and EBIA. Actually, they're more than that. They're kites. So we have two kites.
Is F the reflection of J?
Yeah. I mean,
so,
you could.
Yeah, sure.
Oh yeah. So I mean, yeah, like you could define, like F is the circumcenter of B prime CD, J is the circumcenter of BCD, and they're basically reflections across CD, like you said, because those two triangles are congruent.
So the two triangles are congruent, and they also might have the equal radius.
Yeah.
So that makes JDFC a rhombus, I guess.
Yeah. So JDFC is a rhombus. Could you please move B? Oh yeah, it looks a little collinear with CC prime. So let's see. Whoops. I don't like that. Yeah, that's a little better. Okay. Yeah, now G and N are kind of close together. Let's see if I can make that a little better. We'll just leave it like that. All right. Let me just check something for a sec. Yeah. Okay. So yeah, we have two rhombuses, and it's like the endpoints of those rhombuses form a trapezoid. And
And I think KL is parallel to BC is parallel to AD because K and L are the midpoints of the of the trapezoid.
yeah, that's true. KL is parallel to BC and AD. That seems like it would be helpful. So yeah, it almost looks like G lies on BD, but it's hard to make it so that it doesn't look like G lies on BD. Yeah, so on the one hand, I don't want G to look like it lies on BD, and I can do that, but then it looks like B, C, and C prime are collinear. Oh well. Let's see if there's a better way. Maybe that's a little better. So yeah, we have the midpoint of the center of two circles. What? I mean, that means that the difference between the powers is the difference between the radii, right? So yeah, I feel like there's a good chance that there's some kind of a power of a point trick here. So yeah, how can we use power of a point somehow? We have two rhombuses. Maybe we could even use the gliding principle. Because we have three midpoints, right? We have all these midpoints. Maybe we could even use Desaards theorem, because if you have triangle EBA oh, but I think it's kind of like we already did use Desaards theorem. Yeah, we have 3 midpoints. It feels a lot like the gliding principle, doesn't it?
Sorry, what's the gliding principle?
Yeah, so if you have 2 similar triangles, it's like if BEA and C, I don't know, C and CJD were similar, which they're not. But if you took the midpoints of corresponding vertices, they would form another triangle that's similar to both of them. So I guess I kind of wonder, can we find the point such that BEA is similar to CXD? So since BC I kind of like that approach, but I'm just trying to figure out how it would work. So let's see, angle BIA is twice angle BCA, and angle CJD is twice angle CBD. We should label the midpoint of IJ. All right. Let's call this P instead. So yeah, so G is the midpoint of EF and K is the midpoint of IK. So GK is parallel to IF and GL is parallel to EJ. KGLP is a parallelogram. All right. Well, yeah, we have like a lot of parallel lines here. I don't even know if we need points K and L. Like, let's just use the centers, right? I mean, maybe it's useful. I don't know. But
No, it is a parallelogram.
it is a parallelogram. But like,
yes, I can prove KI parallel to GL, because if you see triangle IEJ, so KL and are the midpoints, and of course KI is parallel to EJ. And similarly, if you look at the triangle EJF, G and L are the midpoints, and that is also commonly parallel to EJ, and that
yeah,
is symmetrical to the other sides.
Yeah, so yeah, for that reason, no, it's definitely a parallelogram. P and G are reflections of each other across the midpoint of KL. So since P is equidistant from B and C, then we're saying G has to, I think that does solve it. I'm just thinking through it for a sec. But yeah, I think since PKGL is a parallelogram, like Sai mentioned, I think that finishes it. Just thinking how to rigorously prove it, because P is equidistant from B and C, right? And so by symmetry, it means G has to be equidistant from AB. How do we make that like rigorous? I'm just thinking. It feels true. So PB equals PC. Yeah, but so I agree, like we reflect P across the midpoint of KL. And we get G, but then how do we get why does that mean GA equals GD? It feels true, I agree with that, but G will go to P. I agree with that. And AD will go to a line parallel to BC. So, okay, let me draw that midpoint. So if I reflect A across O, so yeah, I guess it's kind of like, so we want to show PA prime equals P, I guess we know PA prime equals PD prime. And so if PA prime equals PD prime, yeah, okay. Or no, we want to show PA prime equals PD prime, but I'm just thinking in my head how I'm going to write this out later. Since PB equals PC, PA prime has to equal PD prime. Okay, I'm gonna write this out. So yeah, are there any parts of the diagram that we can delete? I don't think so. I think we want everything we added. So I'm gonna delete it for now, but I'm gonna add it back as I do the proof. Okay. All right. Well, let me see. All right. Okay. Let me try to shrink this a little bit to make more room for proof. Yeah, let me just shrink some stuff. But that is the solution. So all right. So we want to let I be the circumcenter of ABC and J be this. Okay, so So draw those two circles.
What is this competition? Tuymaada sounds like a disease name.
It's in Russia. It's for advanced high school students. I think, I'm not sure if students from other countries can participate, but it's held in Russia every year. And this year, because of COVID, they did only, it's actually for science competitions, not just math, but it's also like physics, chemistry, and other things.
So, so the paper is composed of all physics, chemistry, and maths.
And maybe some other science, I'm not sure. But I think they have like a separate competition for each kind of science. So
Wow, that's tough, man. Because this question looks like an some national level Olympiad questions, and national level Olympiad questions should be a separate entity, not with a mix with science Olympiad questions and all.
yeah. So it looks kind of hard. Yeah, it's going to be hard to get a perfect diagram here, but all right, I'm just going to try to write this up quickly. So let H be the circumcenter of ABC and I be the circumcenter of ABC. All right. I'm going to break that into two lines. Okay, and then we form the parallelogram. So all right. And P, let P be the midpoint of, or I'll just see what it's called. So where's my midpoint? So L is the midpoint of each. And then we claim, was a parallelogram? LJGK is a parallelogram. So I'll just say JL is parallel to IE since it's a mid-segment of HIE. So JL is a mid-segment of HIE and GK is a mid-segment of FIE. Okay, so see if that fits on one line. I would think it should. It overlaps it a little bit. Oh well. So that means that JL is parallel to IE is parallel to KG. And then similarly, KL is parallel to JG. And that means that KLJG is a parallelogram. All right. So we could draw that in. And yeah, the midpoint of JK, so now it's starting to overlap stuff, but so L is the reflection of G across the midpoint of JK. So so let N be the midpoint of JK. So then the reflections of A and D, so let A prime and D prime be, so first I'll say, yeah, L is the reflection of G over N. And then let A prime and D prime be the reflections of A and D over N. All right. So that means that A by symmetry AB A prime D, I'll just say by symmetry A prime M equals D prime M. And that means that L A prime equals L D prime. And that means that GA equals GD. All right. And that is it for this problem. So I'm going to move to the next one. All right. Oh, I thought that was our fourth problem for some reason. I guess it was only our third. Yeah, right. Okay, so here we have a rectangle. What's the best way to draw a rectangle? So like this, whoops. Okay, yeah. Whoops. That's problem 3. You got a screenshot? But yeah, you'll be able to see it on YouTube pretty soon. All right. So here is our fourth problem. This is not working like I wanted it to. Okay, so there we go. So C, and then so we have a rectangle ABCD, and a point E is on the extension of side AB, and EC, let's draw the circumcircle of AB circumcircles ABE, and we see where EC meets it at a point F. DC and AF meet at P. Let's see if I can make this lie on the diagram better. So EC and AF, DC and AF meet at a point P. H is the foot of the perpendicular from C to the line through E and parallel to AF. So and we want to show PH is tangent to the circle. Okay. So I will hide some stuff. I haven't even drawn PH yet. Okay. So EH is parallel to AP. There we go. Okay. Whoops. We want to show PH is tangent to the circle. So we don't know yet that PH is tangent. We want to show it. All right. Okay. What's a good strategy here? So is that point of tangency special at all? Is there something about it? Are B, C, and G collinear? They look like it. So it looks like really we could let BC meet the circle at a point, and then we want to show that P, G, and H are collinear. And maybe we have like a lot of cyclic quads here. So let's see. Yeah, this might be a fast one. This might not take a huge amount of time. So DEHGC is cyclic because those are all right angles, right? And then can we show CGFP is cyclic? Yeah, because it has two right angles. And then we just need to show that PG and H are collinear, which is, I'm sure, just an angle chase. And then it's probably also an angle chase to show their tangent. We're done. Okay.
That was a quick one.
That was a quick one, wasn't it? All right. I'll write it up super quickly, as fast as I can. Should I even bother writing it up? Or let BC meet omega at G. Angle CDE equals angle CHE equals angle CGE equals 90. Means that CGH is cyclic. All right. So we can draw that. And angle CF and angle GCP equals angle GFP equals 90. Since AG is the diameter. That means that GCFP is cyclic. All right. And then then we could show those are collinear. So we have an angle PGA or angle PGC is equal to angle CFA is equal to angle EFA is equal to angle EGA so we want to show PGC is 180 minus HGC. So EGA how do we do this? I'll just write that out so far. So PGC CFA is EFA. EFA is well EFA is CFA, which is wait, I'm getting confused here. Okay, so you know what? It's not that hard. We could just show PGF. Okay, I'm just going to write it like this. PGF is PCF, which is maybe this is harder than I thought. PGF. Yeah, I'll do it like this. PGF is PCF, which is angle PAD, which is equal to angle FAE, which is 180 minus angle FGE. So PG PGF is PCF, which is the same as, no, we don't know PCF is PAD. Yeah, I think I'm missing something here. I have to use the parallelism. That's what I keep forgetting. Okay, so once I use the parallelism, I think I should be good. So we have angle CGH is here's, okay, I think I got it. 180 minus angle, that was my problem. I wasn't using the parallelism, which is 180 minus angle EFA, which is angle PF So 180 minus angle EFA is 180 minus angle PGC. All right. I was just in a rush, so but that is an easy answer. So PG and H are collinear. And then we want to show its tangent, and that pretty much that has to be an angle chase. So angle PGC is so angle PGB is PGC, which is CFA, which is EFA. Yeah, okay, it's an angle chase, yeah. Okay. PG, I'm just gonna write it the way Hakan said. So just thanks for letting me copy paste. So see how this works in LaTeX. That's not so bad. So angle PGC is AFE, which is half of arc AE, which is arc BG. So that means that PG, or I'll just say that means PH is tangent to omega. All right. Now I will move on to the next problem. That was a nice, easy one, a break from some of the harder ones. So thanks everyone for your help. All right. So, oh, this one looked interesting. We have a cyclic quad ABCD. So yeah, I'm probably another 40 minutes here before I finish. So we have a cyclic quad A, B, C, D. Got some more choices here. So A, B, C, D, and we want to A, B, and C, D meet at P. A, D, and B, C meet at Q. Very familiar configuration. That's P. That's Q. We want to show the orthocenters of APD and AQB. The distance between those orthocenters or the distance between these orthocenters. So triangle center APD4, and then triangle center AQB4. I don't even see it because it's like off the page. And then triangle center CQB4. That's also off the page. And then triangle center BPC4. That's on the page. So some of the orthocenters are on the page, some are off the page. Maybe if we shrink the diagram enough, then they'll all be on the page. In fact, they look collinear. In fact, I think Rodrigo showed me this once. If Rodrigo is on right now, I think he would, he might have a solution immediately, because I feel like, so is that what that is? Is that the Steiner line? I'm not sure what the Steiner line is, but is that what it is? I know Rodrigo has shown me this line. So basically, we're saying that HF is equal to EG. Let's see. So APD is E and AQB is F. We want to show EF equals GH. Okay. Let's draw. So we have the Mikkel configuration, right? So we could draw all those nice circles. Whoa. Oh, because I drew an arc and not a circle. I was gonna say. All right. We have lots of Mikkel circles here that all meet at P. Where's my last one? PAC, I think, is the last. Oh, I'm sorry. Oh, ABQ. Oh, yeah, ABQ. Sorry. So for collinear, now we have to show the distances. Let's see. Why are they collinear? Okay, so it has to do with so by the theory of Mikkel, the Mikkel point Pi and Q are collinear, right? Whenever you have a cyclic quad, the Mikkel point is like collinear with P and Q. And so the circles with diameters AC, BD, and PQ are coaxial. Okay, I'm going to take that theorem for granted for now. But how do we know the distance PFE is equal to the distance GH? Can we use Casey's theorem? But yeah, they're orthocenters, not circumcenters. So how do we get the distance between two circumcenters? I'm sorry, the distance between two orthocenters. So yeah, I'll draw those three circles with diameters BD, AC, and PQ. Yeah, like the proof, I know the proof of the Gauss-Bode-Miller theorem, it involves the orthocenters, right? And it's like you do something with like powers. Back to recording and seeing what happens. All right. So it is recording. All right. So yeah, there's like a lot of theory in this problem that I'm not super familiar with, but you're saying all these points lie on the common radical axis of those circles with diameters BD, AC, and PQ, right? So then how do we show the, it can be proved by power of a point. I think I've seen that proof before. But once we know that, is it obvious that the distance EF equals the distance GH? So that also can be proved by power of a point. Write out the steps. How do you prove that? Oh, okay. All right. So the reflection of the orthocenter over the side lies on the circumcircle, right? So if I reflect E over AD and I reflect F over AD, so basically I want to show BJ is equal to this is interesting. So if I reflect F and E over AD, I get B and J. And if I reflect G and H over CD, then I get I'm a little confused now. So do I want to show BJ equals LK? Hold on, I'm going to read your comment in a second. Yeah. Oh no, they're close but not equal. I'm going to delete what I added. Just look at what you're writing. If ABCD is cyclic and X and Y are the orthocenters of ABC and BCD, and AXDY is a parallelogram. All right. Do you guys mind if I move on to the next question? Just because I think this one involves like a lot of theory, and I think I'd like to research it after. But do you guys mind if I move to the next question? All right, sounds good. So yeah, maybe we can knock this one out quick. This one looks like it might be easier. So we have a triangle ABC. B1 is the reflection of B over line AC. And okay, so we draw a bunch of reflections. And this is kind of a familiar configuration in a lot of my videos where we reflect B across AC and C across AB. It's getting cut off a little bit, but there we go. And O1 is a reflection of the circumcenter of ABC across BC. Or I'll call that O. O1 is the reflection. I'm just going to call them, instead of 1, I'm just going to do it prime. Okay, so, whoops. We want to show the circumcenter of AB1 or AB1C1 lies on the line AO1. So all right, let's see if I can make it like there we go. So we want to show D lies on AO prime. Interesting. Yeah, let's do something more like that. Okay. All right. So these are both kites, and okay, so how would we show that those are collinear? B C prime O and B, they're congruent, and B C O prime. No, I don't think so. But there might be other congruent triangles. This almost feels like a Semidian problem a little bit. So let's see. So I wonder, let me draw the circumcircle. Let's draw some stuff here. Is AD an angle bisector? I don't think so, but let's see. Yeah. Yeah, we could try drawing the point, the antipode of A. So I think let's see. If we draw the point such that makes a parallelogram, Yeah, I mean, basically we're saying if we want to show that A, B prime, A prime, C prime is cyclic, is kind of what we want to show. So yeah, we kind of take the midpoint of BC, and then let's see, is that an angle chase? So I kind of want to draw. I mean, yeah, basically, I think it's equivalent to showing the reflection of Okay, let's just, basically we want to show A prime CA is 90 and A prime B prime A prime C prime A is 90 and A prime B prime A is 90. So I mean, really, we can ignore a lot of the figure. But basically, we're saying if we reflect C across AB and we draw the point so that makes a parallelogram, then we want to show that that's a 90-degree angle, which feels like it shouldn't be that hard. Yeah, because let's see. So this angle right here is 180 minus A, and this angle is B. So this is, so if you have 180 minus A and then you have B, then this is going to be 180 plus A minus B. So yeah. This angle is 2B. So yeah, you could also think about it as 2B plus C if you wanted. I'm just sort of rewriting it in my head. But angle AB A prime is 180 minus A, I guess is what I was saying. Or angle. So C prime BC is 2B, right? But AB A prime, I was saying, is 180 minus A. AB A prime, because this angle, yeah. But I mean, all we want to show, so I'm just going to hide a bunch of stuff. All we want to show, we don't even need a lot of points in this figure. All we have to show is that in this configuration, angle AC prime A prime is 90 degrees. If we can show that, that solves the problem. And it doesn't that look like it should be simple? Look at how simple that is, right? There has to be a simple way to show that, right? Doesn't it look like there just has to be a way to show that AC prime A prime is 90? Let's see. Do we have like a spiral similarity? I think we might. So does a spiral similarity take AFC to A prime C prime A? No, those don't look that similar. I'll just do a quick check. 20.9 and yeah, those aren't necessarily similar. A prime C prime or A prime C doesn't look like a parallelogram. Yeah, you're actually it kind of doesn't. Okay, I think I was wrong about that. I think you're right that it's not a parallelogram. Okay, scratch all that. I don't know why I thought that. But yeah, I mean, I guess yeah, this looks like a very So does the reflection of D over BC lie on this circle? No. So let me do this. Yeah, what if I did reflect A across the midpoint of BC? tricky. All right. So AE is a median in triangle AOO prime. It's kind of like we want to show E lies on the median of, so like if I take the midpoint of well no, that wouldn't necessarily work. Let me draw the orthocenter of triangle ABC. Oh, whoops, I want that to be 4. So the orthocenter and the circumcenter are our orthogonal conjugates, right? And when you reflect the orthocenter over the side, it lies on the circumcircle. Yeah, I'm not sure what that does. Yeah, this is a tricky one. This is harder than I thought it would be. It reminds me of a lot of other problems on my channel though. Like I think I showed, what did I show? In this configuration, so there was a previous problem on my channel where I showed if you take the tangents at B and C, so we'll draw it like this. So F, I think I showed that the circumcenter of FBC prime lies on the altitude from A. So I wonder if that could be used at all. Is A, F, B prime, C prime a parallelogram? So I'm gonna wrap up soon, but I think, I wonder if A, F, B prime, C prime is a parallelogram. No, doesn't look like it. Yeah, so if that's not true, then I'm not sure. But yeah,
Maybe
complex.
we can look for a hint.
Yeah, complex
if that's a
number.
solution.
Or what did you say?
We can look for a hint.
Yeah. I think I'm gonna, so yeah, see if you can figure it out using complex numbers, and you could post it on Discord if you end up finding it, or my YouTube channel. So we're reaching 1 p.m., so I think I'm gonna stop right here. But this is a tough one, but thanks everyone for participating. So have a good one.
Thanks, Michael. Please subscribe.
Like and subscribe. Yep.